So yesterday we discussed about data link layer. Major part, major jobs of the data link layer are framing, error control, flow control, and access control. When we talk about framing, it is a process in which we divide our data into smaller parts. In each frame, we'll be inserting one header and a trailer. In the trailer, we might be having checksum, parity bit. In the header, we'll be having the MAC address. So there are various ways through which framing can be achieved. One of them we have discussed yesterday is character count, that you insert a character and then those many characters will be there in this frame. Whatever is the first character of the next one, those many characters will be there in the next frame. Again, the next will be treated as the count and so on. If the count itself changes, if 5 changes to let us say 7 or 8, then the track will be lost. Not only for this frame, but for the subsequent frames also. So all the frames will be all the frames will not be correctly determined by the receiver, and from the transmitter we will have to send all the frames again. So that violates the basic idea of framing. Framing was done so that whichever frame is problematic, only that can be resent. So we said that this character count is not a very practical approach through which we will be able to deliver data efficiently. So the next one was byte stuffing. In byte stuffing, we insert one byte in the beginning and one at the end. So whenever this flag byte, if that appears in the data, at that point of time, receiver may be confused whether that is end of the frame or that is the data. It will unnecessarily treat this frame as end of the frame. So we will be discriminating between frames, flag bytes, by inserting one escape here. Whenever there is a flag byte, one escape is to be inserted. So receiver will be coming across two type of flags, one followed by escape and one direct escape. If escape is directly if flag is directly coming, then it will be marked as end of the frame. If it is followed by escape, then escape will be removed and flag will be preserved. So up to this point we had discussed yesterday. Do we have any doubts on this? Okay. So here, can you think of any problem? Will it work in all the circumstances, or in some circumstances it might fail? Is it a foolproof method which will address most of the circumstances? Like if your flag byte changes to something else, then after some time, two flag bytes will come together. One for end of X frame and one for beginning of X plus 1. So whenever there is occurrence of two flag bytes together, then we can know that one was end and one is the beginning. So synchronization will be again achieved. It is not lost forever. Do you think it will work in all the circumstances for all type of data? I've asked a question that the method which you understood, can you see any problem with that, or you think it will work for all type of situations? Yes, So here if escape characters are more, then those many escape characters we will be inserting. Here there are two escape characters. So before one escape, you are going to insert escape. Before flag, we are going to insert escape. So whenever there is occurrence of escape or flag, we will be inserting one escape before that. So here it will work. It is a foolproof method, but it is not efficient. As you said, if escape characters are occurring very frequently, then each time we are inserting one escape. That means in your data, if let us say here out of 4 times, 2 times it is occurring 50% of time, then those many percentage you need to insert the extra bytes. So here overhead is higher. It works fine, but it is not efficient. So we have the next technique, which is bit stuffing. So all of you, please listen to me what we are doing in the bit stuffing. Another limitation of this is because here working with a byte boundary, we are working with one byte like A, flag, B, etc. If someone is functioning with some different coding mechanism in which A is represented by 7 bits, B is represented by 7 bits, and so on, at that point of time, this byte boundaries will not function. So here in bit stuffing, we are dealing with bits. So doesn't matter whether you are working with 8-bit boundary, 7-bit boundaries, or you have your own coding mechanism through which you are going for 6 bits for each of the character. Then also because we are going to deal with bit string, it will work. That is one advantage. Now here, please pay attention. First, we will convert our data into bit string. Initially, one byte is inserted. What is the byte? 0, 6 ones, 0. Always you insert 0, 6 ones, 0. This is the delimiter which will be inserted in the beginning and it will be inserted at the end. Whenever any data is to be sent, always you will send this, then data, and then at the end this. So again you may ask that what if this is part of the data? This can very well be part of the string. Then again our receiver might be confused whether that is end or not. So here the solution is very simple and elegant. What is suggested that whenever you are sending your data, start counting number of ones. Here 2 ones, so you are fine. 0, so you will reset the counter. Again you are counting here 1, 2, 3, 4, 5. Whenever there are 5 ones, insert 1 0 after that. Reset the counter, again start counting 1, 2, 3, 4 and 5. After 5 ones, 1 0 will be appended. Again after 5 ones, 1 0 will be appended. Why do we do that? Because for this pattern to take place, you need 6 consecutive ones together. Whenever you have 6 consecutive ones, then there is a chance that this starting or ending delimiter might be present. But we are not giving any opportunity for it to take place. So whenever there are 5 ones, you are inserting 1 0. Receiver, after 5 ones, 0 always will be removed. So after 5 ones, even if you have 0, then also will append 1 0. Receiver will be removing that. So whenever receiver is receiving this string, what it will do? It will receive 0, 1, 1, 0. And then it will count that, okay, these are 5 ones. That means this 0 was stuffed. It was inserted. It will remove that. Again, it will count 5 ones. It will preserve them. This 0 which was inserted will be removed by the receiver. This will be removed by the receiver. So what is advantage of bit stuffing over byte stuffing is, here if this pattern takes place, let us say 8 times, then we are inserting 8 bits. At each point of time, just 1 bit is inserted. That means 8 bits, 1 byte. While in the earlier scenario, if you are having 8 occurrences of either escape or flag, then 8 bytes will be inserting, 64 bits. So byte stuffing was pretty heavy, while here it is feasible and it is simple. We are not going back for 6 zeros to take place and then we go and insert. Why? Because it will be very difficult that first you are taking care like 5 ones, then 6th one, then you will go back and then insert here. You will have to store that and process data twice. Rather than that, it is much simpler that whenever 5 ones are sent, you insert 1 0. 5 ones are sent, insert 1 0. So that there is no chance that 6 ones will be together. And if 6 ones are not together, then 0, 6 ones 0, 6 ones 0. That pattern also will not be taking place. So bit stuffing is the technique which is frequently used for framing. Have you understood this? Yes, Keval. If after 3 ones you have a 0, then you will reset the counter. Whenever you have 5 ones together, then you will insert 1 0. Otherwise not. That's it. So this technique is efficient because we are inserting just one bit. We are stuffing just one bit. And on the top of that, we are not following byte boundaries. We are following bit stream. So it is flexible to be used across the various formats. So if you have no doubts about framing, then framing is done. We will start with error control. Feel free to ask me if you have any doubt in framing, any one of you. Have you all understood framing? No, we are not checking whether data is correct. That is part of the error control. Currently, we are focusing on whether we can differentiate the frames. That is in the framing. In the framing, we say that this is the first frame, this is the second frame, this is the third frame. Then is receiver able to differentiate between the first frame, second frame and third frame? Then frame is correct or not? That is in the error control, which you will see soon. No, you don't append this in the data hash. You just append 1 0 after 5 ones. If what you are writing is data, let us say you are saying that this, okay, this is same as 0610. You said that only. If this is the data, then what you will be actually sending, you will be sending first the starting delimiter, then 0, and then again at the end, this is going to be, there will be no space. Okay, I'm just doing it so that you can easily understand. For an example, if this is your data, then you will be inserting starting delimiter 0, 5 ones, 0, this 1 0, and then the ending delimiter. If shell you have 5 ones and 0, then you will be sending 5 ones and 2 0. One appended 0 and one will be as it is. After 5 ones, whatever is there, 0 or 1, that will be there. We are going to stuff one extra bit. That's it. At the receiver, after 5 ones, 0 when it is encountered, always it will be removed. Regardless of whether after 0 you have a 1 or a 0, this 0 will always be removed. At the transmitter, we are always inserting that. At the receiver, we are always removing that. Okay, so again, any doubt? Is it clear? If you have any question in framing, feel free to ask me, any one of you. Kanal, Kaushal, Jenil, Deepak, did you understand this? The names which I have spoken, are they here? Okay. So now we are talking about error control. Okay, before I continue with error control, yesterday I have asked one question for you to figure out. Yesterday, as in the last class. Do you remember what the question was? I have raised a question and asked you to figure out the answer. and I said that we would discuss in the next class. Yes, the question was this, that if MAC address is unique and if IP address is unique, why do we require both of them? And we have third address as well. Which is the third address? Port address. So if we have IP address and if we have MAC address, do we require port address? Yes. So we have no doubt that port address will be required because IP address and MAC address are of the system. While once you reach the system or the destination, that is not sufficient. On that host, we might be having multiple applications being executed parallelly. So we need to address the applications as well, and port address is doing that. Port address is an entity of which layer? Transport layer. Nice. MAC address? Data link layer. Network address? Oh, sorry, IP address, that is of the network layer. Okay. So, is there anyone who would like to answer that why do we require IP address and why do we require MAC address? You can unmute yourself and answer it. It might be difficult to type the longer answer, so you can unmute yourself and discuss. So Keval says that MAC is for local identification and IP is for global identification. So in MAC address, let us say, if I say I have one MAC address and someone in Haryana is also having a MAC address, and then someone in Canada is having the MAC address, will these three MAC address be same or different? They'll be different, right? Globally, MAC addresses are unique. Then why cannot we use MAC address only to deliver data from someone here to, let us say, Haryana? I want to send someone sitting in Haryana a program. So will I not be able to do that? Why do we require both the addresses, Abhi, IP address and MAC address? Both of them are unique. So why do we require them? What do you mean by exact delivery? Otherwise, exact delivery will not be taking place. So Shell is saying that MAC is identifying the device and IP address is identifying connection to the network. So if you just MAC address, let us say, then will you not be able to identify the device in Haryana? Okay, so everyone, the answers which you are giving are not. Yes, Keval, please.
Hello, ma'am, am I audible?
Yes.
Ma'am, as you have given example that one MAC address is Haryana, one address is here, one address is Canada. But if we want to talk with this address, then we need internet connection. That internet connection is, I think, provided by the IP address because it is the part of the network layer. But the MAC address is the part of data link layer. So I think we cannot talk to this persons in the sitting in Canada or Haryana without internet.
No, internet is required. I agree. Like, what is internet? When I say internet, that is internetworks. Like, there is one network here. Our network is connected to probably one network in Ahmedabad, is connected to one network in Mumbai, is connected to one network in Haryana, and so on. So all the networks are connected with each other, and that we say is an internet. Okay. So of course, our devices through devices between which we want to establish communication, they must be in networks and the network should be connected, so they should be on the internet. That is one thing. And now Okay, before I talk to you, Keval, everyone. So, when you are writing something, most of you are writing which is correct, but it's not, sufficient or rather convincing. So, my aim is that you will be able to find the answer where you think over that, you argue with yourself or the answer which you are reading, and then you try to figure out that why so. Okay, so again, back to Keval. So in that case, let us say only IP address. We can remove the MAC address. If you say that you are on the internet and the network layer is connected and IP address is at the network layer, then if I have just IP address, because IP address is unique universally, right? Like the person sitting in Haryana and I will never be having the same IP address. So using IP address, will we be able to communicate successfully?
Ma'am, I think not, because the we need, means we talk with, mean we want to talk with the person, then we need some data of that person. So at that time the MAC address is also required.
Data of a person means identity of a person. That is what you want,
Yes,
is identity
yes,
of the
ma'am.
system.
Yes,
So
ma'am.
IP address provides that. IP address of that system is unique.
Okay. Hmm.
No one in the world is having IP address of the person of Haryana at the same time. If he is having IP address, let us say 12.13.14.15, then that is unique to him only. No one else is having that. So when I send data to 12.13.14.15, then he is the one who will be getting the data and no one else. No, no, I don't want you to say, okay. So everyone, I hope you realized that you have searched and you have got the answers, but probably you are not fully convinced or you didn't understand or grasp the concept fully, and that is perfectly fine. I want to explore, think, and then be convinced with the answers or the solution or the reasons or justification. So in this subject, if we don't do two or three topics, that is fine according to me, as long as you develop the insight. I want you to develop the insight of the subject, that why it would be like this and why it would be like that, rather than giving you details that, okay, here is this, here is the structure, here is the method. Rather than that, we would be going for the reasons and justifications. So Rikin says that, no, Rikin, see, probably you can answer like this. Okay, everyone, what you are saying is not incorrect. But what I want is, if you have only MAC address, then this is the problem which you will have. That is why IP address cannot be avoided. And if you have only IP address, then this is the problem which you have. That is why MAC address cannot be avoided. I want to answer like this. Am I making sense? Okay. So here, I'm asking you that why do you require food and why do you require water? Then I'm asking you rather that why do you require food and water both? So you are saying that food is required for the energy and water is required to, I don't know actually. Water is required for the digestion. Let us say something like that. So I want you to tell me that if you don't have this, then this is the problem. That is why this cannot be avoided. And if you have this, then this will not be problem. Yes, IP will keep changing. That is true. Then let us have only MAC address, Harsh. MAC address will not change. Harsh, can we just have MAC address then? So that is so channel. If it has geographical information, then what? Say if you know the. Okay. So can I again postpone this question for the next class? All of you, please search in a better way. Read a little bit more, like spend 10, 15 minutes, half an hour. Try to think over that. If needed, you can argue with yourself or your friend, and then again we will discuss in the next class. So will you be doing it? Okay, fine, great. So now let us again start with error control. When I say error control, then we don't actually go over the communication link and control the error. However, the link which is generating errors will be affecting our data. So we have mechanisms through which we can overcome the effect, we can overcome the adverse effect caused by the errors. That is what we do in error control. So we are not literally controlling the errors, but the way it is harming our data, we try to overcome that. That is what we do in error control. So there are two type of algorithms in error control: error correcting codes and error detecting codes. When I say error detecting codes, that means when you send your data, then receiver will be receiving the data. It will be able to identify whether there is an error. It will be able to detect the error, but it will not know where the error is. It will know that this code is wrong, but it doesn't know what is wrong. Do you know any example of error correcting codes, error detecting codes? All of you are aware of one example of error detecting codes, parity bit. Yes. So when you use parity, yes, Hemming code. How do you know about that Hemming code? Where have you learned it? CSA is in not SEM 2. Is it in SEM 2? SEM 4. Okay. Okay, fine, fine. Yes. So those are also error correcting codes. Checksum is a generic term, Bhavik, which is used like anything which is helping you to find out the error. We can say that is a checksum. Now, in case of error correcting codes, when the receiver receives data, it will not only know where the problem is, it will also find out that which bit is problematic. And once it knows that which bit is problematic, then it is very easy for it to change the bit. Like if it is 1, it will be making it 0. And if it is 0, it will be making it 1. So, error correcting codes are not only for finding out the error, but it can also find out where the error is, and accordingly it can correct it. In case of error detecting codes, only error will be detected, it will not be knowing where the error is. Now, whenever I say we are dealing with error control, then always will be having redundant bits. When I say redundant bits, what is meaning of that? Additional bits or extra bits which is not part of the data. Our aim is always to send the data. When you want to send the data, then out of those bits, you will be providing some extra bits. And those bits will be helping you to find out whether there is an error. Like in parity bit, our data would be there, and at the end, we'll be having one bit which is the redundant bit or the extra bit or the additional bit which is used for the error control. Now, there will be key matrices in the error control, like your code will be having a limitation of how many bit error can be corrected or how many bit error can be detected. No code is providing you infinite capability that any number of errors can be changed. And what is the burst length of that? Burst means together. Like here, if I'm having this series, then if we are saying that it is capable of correcting three random or scattered bits, that could be one measure. Like 3-bit error can be detected if they are not together, while some will be providing having like, even if you have burst error, that means consecutively 4 bits are corrupted, then also you will be able to detect that. So how many bit error can be corrected or detected, and what is the burst length against which your algorithm is immune? Now let us talk about hemming distance. Okay, so hemming distance, if I'm giving you two codes, A is 0 0. Okay, A, whenever I want to send A, I'm sending 0 0, and whenever I want to send B, I'm sending 1 1. So here, A and B, how many bits are different in them? Then 2 is the Hamming distance. Okay. So Hamming distance between two code word is number of bits that must be flipped to change from one to other. Like here, if it is 0 0, if I change both the bits 1 1, then only it will be confused as B. If I change just one bit, then it will be 0 1 or 1 0. Then there will be no trouble. So in the simpler language, I can say that the difference through which all the code words are different from each other, that is the Hamming distance. Now, if I say that C is 0 1, then what is the Hamming distance between A, B, and C? C. Between A and B, it is 2. Between B and C, it is 1. And between A and C, it is 1. So, then it will be 1. Whatever is the minimum difference between all the possible pairs, that is the Hamming distance. So, Hamming distance in this scenario will be 1. We will be finding out distance between all the codes. In whichever is minimum, that will be the Hamming distance. Can you tell me what will be the Hamming distance between this? The new values of A, B, C which I have assigned. No, it is not 2. It is 1. Why 1? Because B and C are different by just 1 bit. Whatever is the minimum between all the possible pairs, will be considering that. Tell me, what is the difference now? One or two? Why one? Okay, what is the difference between A and B? Yes, A and C is 1. Yes, A and C is 1. That is why you said it is 1. Last one. Can you tell me what is the difference now? What is the Hamming distance now? I'll not use the word difference. That is for understanding. The technical word is Hamming distance. What is Hamming distance between A, B, C now? Yes, it is 2. Okay. So now, uh, okay, let's take this example. Hmm, A is defined as 0 and B is defined as 1. A is defined as 0 and B is defined as 1. So now if I want to send AB, I'll be sending 0, 1. If the voltage level is dropped of 1, then my receiver will be receiving 0, 0. Here, this bit is changed. It is erroneous. So I'm getting 0, 0. So what will receiver think? That AA was sent. That means wrong message has been detected. So I can say that if Hamming distance is 1, then I cannot detect 1 bit error. Do you agree with that? Yes. So let us Kaushal try 2-bit error. A is represented by 0, 0 and B is represented by 1, 1. So now what is the Hamming distance here? Hamming distance is now 2. So if I want to send AB now, I'll be sending 0, 0, 1, 1. Now if one of the bits is changed, let us say 0, 0, 1, 0. The last bit is corrupted. When receiver is receiving this, it knows that 0, 0 means A, but it doesn't know what 1, 0 is. So it will say that, okay, here there is something wrong. I'm not expecting this. So here we can detect 1 bit error. So now if Hamming distance is 2, I can detect 1 bit error. Can you tell me a generalized one, that if Hamming distance is, or rather, if I want to detect up to n bit errors, then what should be the Hamming distance? If I want to detect n bit errors, then what do you think should be the Hamming distance? Yes, exactly. N plus 1. If it is n plus 1, it should work. Even here, it is very simple logically. Like n, you want to detect up to n bit error. That means even if your n bit changes, this code should not be same as the other code. That is what you are demanding. But they are different by n plus 1. So even if n bits are changing, the plus 1 bit, one extra bit, is making sure that this code is different from the other code. And hence you will be able to differentiate between them. And as long as we can differentiate between them, as long as one code doesn't convert in the other code, we will not be mistaken. And we will be able to say that, hey, there is something wrong here. So I can say that if you want to detect up to n bit error, then n plus 1 is the Hamming distance. Are we good so far? So if our Hamming distance is 12, how many bit errors maximum can be detected? Can I detect 6 bit errors in that case? Of course, right? Of course we can do that. So now this was error detecting codes using Hamming distance. Now let us talk about error correcting codes. Okay. So now let us say our A is 00 and B is 1. So when I'm sending A, B, then we'll be sending 0011. Now here there was 1 bit error, so receiver is receiving 0010. So it knows that A was sent, and then if 1 bit changes in A, it can be converted into 10 or 01. Similarly, in B, if 1 bit changes, it will be changing into 01 or 10. So when 10 is received at the receiver, it will not be able to confidently say whether it was B or it was A, because in both the cases 1 bit error leads to this code. So here we are confused, we cannot detect it. Now let us try to see. So that means we cannot correct it, right? I can detect that there is an error, but I cannot correct whether it was A or B. I'll not be able to know what was the original message transmitted. So if I provide now Hamming distance of 3, let me try with Hamming distance of 3. So if 1 bit changes here, it will be either of this. Here if 1 bit changes, these are the possible codes, right? Can you think of anything else? A and B. A is 000 and B is 111. If 1 bit error is permissible, like our channel can have 1 bit error, then A will be any of this and B will be any of this. Is it okay? So now when we are sending A, B, we are sending 000 111. Now if there is 1 bit error, let us say receiver is receiving this. So when receiver is receiving 000, it knows that it is A. When it is receiving 110, it knows that it is likely to be B. It knows that actually ideally it should have been 111. So it will correct it and then it will detect the properly. It will detect the proper message like AB. Because it knows that here we are having number of ones are 2, which is more similar to B than A. So whenever Hamming distance is 3, we can correct up to 1 bit error. If we have 2 bit errors, will we be able to correct it? No, then we'll be misguided. We will think that 100 means it should be A. So We are wrong. And if we are wrong, that means we couldn't do it. So now correcting single bit error requires distance of 3. We saw that if the distance is 2, we cannot correct it. If the distance is 3, then 1 bit error can be corrected. 2 bit errors will not be able to be handled here. So whenever you want to correct single bit error, then 3 Hamming distance is sufficient. Can you generalize this? If I want to correct up to d bit errors, if I want to correct up to d bit errors, what should be the Hamming distance? So everyone is saying that d plus 2. Let us try it. Okay. Our A is 0, 0, 0, 0 and our B is 1, 1, 1, 1. The Hamming distance is 4. Then according to you, how many bit error we should be able to correct? 2. So here 2 bits changes and it converts into 0, 0, 1, 1. 2 bits are changed here, it converts into 0, 0, 1, 1. And here also 2 bits are changed. This 2 bits in this code word changes and it is changed to 0011. So when receiver receives this, when it receives 0011, can it confidently say whether that was A or B? In A, if 2 bits are changed, it will be 0011. If in B 2 bits are changed, it will be 0011. So will we be able to correct the error? We will be able to detect it. We will know that here there is something wrong. But unfortunately, no, we will not be able to correct it. So your quick answer is incorrect. Would you again like to think over that? Come on, now I expect better than this. Huh? You cannot simply say d plus 3 in that scenario. This time, now I want you to figure out for 3 error, will it work? For 3 bits, d plus 3, is it the best answer which you can give for 2, 3, 4, 5, 6, everything? So probably it is time to pick up the pen and book and make your hands dirty. Try to solve in the book and then give me the answer. I'll wait now until you give me the answer after trying. Take 1 or 2 minutes if you like. What is n? I just want d to be present in the answer, isn't it? Like d is number of bit errors which we want to correct. D is the number of bits which we want to detect. Okay, we can probably do it like this. If you want to correct 1 bit error, what is the Hamming distance required? If you want to correct 1 bit error, what is the Hamming distance required? Like this, I cannot say 100. Using 100, of course, you can do it. But I'm talking about the minimum distance, which is sufficient. And it is required. No, if 1 is the Hamming distance, you cannot correct 1 bit error. Like if 0 converts to 1, then you will think that 3. Yes, it is 3. If 2 is the Hamming distance, if you want to correct up to 2 bit errors, then what should be the Hamming distance? We have checked here that if the Hamming distance is 4, then you cannot correct 2 bit errors. If 2 is the Hamming distance, if you want to correct up to 2 bit errors, what should be the Hamming distance? 5. Okay. Now 3, I want you to do it. I want you to do for 3. Find out the answer. I'm waiting for the answer for 3. What Hamming distance do you think should be provided to correct 3 bit errors? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that is 7. Because if it is 6, if it is 6, then again, here 3 bit changes to 1 and here 3 bit changes to 0, you'll be confused. So 7 would be required. So 7, true. Yes, at least 7 means 7. So some of you have given the correct answer, and that is 2D plus 1. 2 correct up to D bit errors. Hamming distance should be 2D plus 1. So this is the approach which we should be taking rather than making hazardous guesses. We should be figuring out by the examples or logic. So is it fine so far? Any doubt, any one of you? Okay, fine. So now, what do you think is better according to you? Error correcting codes or error detecting codes? Yes, error detecting codes are used in the real life because error correcting codes are expensive. Though our intuition might be telling us that error correcting codes are good because we can able to correct the error. Not only detect the error, correct the error. In case of error detection codes, after detecting the error, we will have to convey the transmitter to retransmit the correct data or send it or correct data somehow. So that way we can feel that error correcting codes are good. But when I say error correcting codes, here we just wanted to go for the 3 bit uh, correction. Then 7 was the Hamming distance. If I have A and B, then 7 is 7 zeros and 7 ones can be kept. But if you want to send, let us say A, B, C, then number of length will be increasing. It will not be 7 because Hamming distance is between all the possible pairs. If I say A to Z, small, capital, digits, symbols, etc., then just imagine what will be the code length for each of the symbol. So it is going to be extremely expensive. That is why error correcting codes are rarely used. Most of the time, error detecting codes will be used because they are reasonably smaller. Redundant bits are lesser in error detecting codes. The extra bits will be in moderation as compared to error correcting codes. Like if you want to correct up to 10 bit errors, then 11 should be the Hamming distance. But if you want to correct up to 10 bit errors, the Hamming distance would be 21. And here each bit will be resulting into very long code words. So now there is something for you in the assignment. The second assignment, one is already pending, which is IP address and MAC address. The second assignment is parity scheme using Hamming distance. In the textbook, please refer to the Tenenbaum only, no other textbook or no other books at the moment. This method is explained because in Foroson and Tenenbaum, the method is explained different way. It is explained differently. So I want all of you to understand the same method, follow it from the Tenenbaum. So here it is given like at the 2 raised to power. If it is 2 raised to power, then you will be keeping your code word, your, what do you say, extra bit there, or the parity bit there. Extra bit or parity bit will be there. And at the rest of the position, we are going to have the data word, and that is how code word is formed. And we will be able to detect errors here. So this you will be doing on your own. Please note it down so that you don't forget it. And now I'll be very quickly teaching you CRC scheme, that is cyclic redundancy check. CRC is also known as a polynomial code. So if we are given the equation x raised to 3 plus x plus 1, if the equation is x raised to 3 plus x plus 1, that means x raised to 3, so we'll be keeping 1 here, x, so we'll be keeping 1, and 1, so we'll be keeping 1. And the term which is not present, of course, the coefficient is 0, so you'll be writing 1 zeros 1 1. So that is the polynomial in this case. So either the polynomial directly might be given, or this polynomial equation might be given through which we can derive this. So now everyone pay attention here, it is pretty simple. Just be with me. So now the frame which we want to send is 1101 01 11011. This is the frame which you want to send. And now the generator polynomial in this case given is 10011. So of the generator polynomial, what is the highest power of x? That is 4, right? This is 4. That means you will be appending 4 zeros after the frame. If here the term is 111, then you will be appending 2 zeros. If the term is 110011, then the power of 5 is there, so you will be appending 5 zeros. So based on the generator polynomial, you will decide how many zeros are to be appended at the end. In this case, it is a power of 4, so 4 zeros will be appended here. The frame means data which we want to send. In the data, we have written our data here, and then 4 zeros are written here. And then this is the generator polynomial. Is it clear so far? Okay. Then we will see here. We will consider first 5 bits because here it is 5 bits long. If the highest bit is 1, then you will multiply with 1. And you will be writing this generator polynomial here 10011. And between them, we perform the XOR operation 0 1 1 1 1 0 0 0 0 1 0 1. Now the remainder for this operation was 1001. This 1 will be taking down. We are checking the highest one. It is 1. So again we are going to keep 1. 10011. We will be doing the XOR operation which will result into 0. Now this 1 is down. Now if you consider 5 bits, it is 0. So we are not going to multiply with 1, but now we'll be considering 0, and you'll be writing 0 here, and again XOR operation. Can you please do in your book? I want you to do it and tell me what remainder you are getting. Come on, quickly open the book and let us do it. Have you started doing? Great. So whenever you have the remainder, please let me know. You will be taking down these four zeros as well, one by one. Is there anyone who has got the remainder? બધા કરો છો ને? Okay. So Harsh has got something. Let us wait for two more answers and then we'll see. You have to simply perform XOR operation and choose whether you will be writing the generator polynomial or you will be writing zeros. It is fairly simple, I think. So why Harsh and Channel you are getting this answer? 111. Here the answer is 1110. Please see where you have made mistake. Yes, Kaval, that is the correct answer. Channel and Harsh, please look at the solution and see. If you have any doubts, of course, you can ask me at any point of time. Okay, now I have started getting a feeling that you have already left for lunch and I'm just talking to the laptop. Is it so or are you still here? Okay, you're still here. Fine. So, get me the answer. Okay, Rikin is getting it. Janil, could you figure out? Okay, Abhi and Love, everyone is getting that. When one, then XOR. Yes. The highest one, if it is 1, then you are going to XOR with, in this scenario, 10011. If this generator polynomial was, let us say, 101, then in that case it would be 101. And if it is 0, then with 0. Yes, Shell, that is correct. So have you all got this? Then I'll very quickly tell you the Next one. Any doubt? Anyone so far? Okay, fine. So now, see, your remainder can never be longer than 4 bits, because if it was 1, then you will be, XORing with 1, and 1 is going to be 0. So maximum 4 bit remainder can be there. If it is just 1, then you will be writing 0001. So here in this case, it is 1110. So what we are supposed to do, this 4 appended zeros which was there, you will replace that by the remainder. So now your frame will be the frame, and last 4 zeros are gone, and instead of that we have our remainder 1110. This is what we have. No, it is in the textbook. Everything is from the textbook, and this time I'm not going to upload because I want you to open the textbook and read it. Okay, so currently let us focus here again. So this is the transmitted frame. This frame will be received by the receiver, and receiver also has the generator polynomial. So receiver will again do the same thing. So everyone, within 2 minutes, can you do it for me? This is the transmitted frame which your receiver is receiving, and now you will use the generator polynomial and follow the same process and tell me what remainder you are getting, and make it real fast, maximum 2 minutes. Okay, so Kevin is now getting 0000. What about others? That is true, Kevin. If there is no error, then at the receiver, remainder will be 0. In this polynomial method, at the transmitter, we find out the remainder like that. Then we append that at the end. And this method works like that only, that at the receiver, if the transmitted frame is correct, then your remainder will be 0. Rikin is also getting 0. So all of you, if you try, you will be getting 0. And then you will also try one thing like 1101. All of you, please corrupt the fourth bit. Instead of 1, send 0. Okay. The transmitted frame is there. Instead of 1, keep 0, and then try to repeat the process at the receiver. This time you will not be getting 0, but any non-zero number you will be getting in the remainder. And whenever you are getting any non-zero number in the remainder, that means there is an error. So this detects at least 1 bit error. Would you like to do it now or afterwards? You can corrupt actually any bit. If any bit changes, then your remainder at the receiver will be a non-zero number, and that is how we can detect the error. But here, so that all of you get the same remainder and we can verify whether you are working properly, I'm asking you to corrupt the fourth bit. The fourth you are making from 1 to 0 and then repeat the process. So I'm asking, are you doing it right now or you will do it afterwards? Okay, fine, complete it. In that scenario, if you are doing it, let us complete it. Okay, so probably you are getting 0 1 1 1. Keval is getting that. What about others? Please do it and then tell me what remainder you are getting. Love and Rikin, what are you getting? Okay, please carry on. Okay, Krish is also getting 0 1 1 1. So probably that could be the answer. If you assume that they have done correctly, Rikin, you are getting 1110 and others are getting 1 1 1. They are different. No, not necessarily you are wrong. Someone else is can also be wrong. Anyway, so can we please conclude here quickly? Moral of the story is that if one of the bits is changed, then you will not be getting zero. You will be getting a non-zero number, which all of you are getting. But ideally, of course, it should be same because we have taken the same example. So if there is no error, remainder will be zero and receiver will keep the frame. It will accept the frame. Whenever any bit is changed, then the remainder will be non-zero and receiver will be able to detect the error. However, it will not know which bit is corrupted. It will not be able to correct it, but it will be able to detect the error and the frame will be rejected. So please do it afterwards your lunch in the evening. And if you have any doubt, you can ask me in the next class. So I'm stopping the lecture now. Thank you.